Welcome to this university-level lecture on partial differential equations. Today, we are going to explore one of the most powerful and elegant mathematical techniques ever developed, the separation of variables method. Whether you are studying advanced mathematics, physics, or engineering, understanding how to break down complex, multidimensional problems is an absolutely essential skill. By the end of this video, you will have a solid grasp of how this method works from the ground up. To understand why this method matters, imagine trying to describe a flag waving in the wind. Its movement depends on both where you look and when you look. Calculating both changing factors simultaneously is incredibly overwhelming. But what if we could split the problem? We can find one rule for the shape and a separate rule for the flapping speed. This is exactly what our method does. It takes a complicated partial differential equation and breaks it down into simpler ordinary differential equations that are much easier to solve. Now that we understand the goal, let us look at the core assumption that makes this entire mathematical technique possible. We assume that our final complex solution can be written as the product of separate independent functions. Crucially, each of these functions must depend on only one variable. For instance, if a function depends on position and time, it becomes a position function multiplied by a time function. By substituting this product back into our original equation, we can physically separate the variables onto different sides of the equal sign. Let us see this mathematical machinery in action using a classic example, the one-dimensional heat equation. This formula conceptually describes how thermal energy moves through a solid metal rod over time. Here, the variable U represents the temperature of the material. The symbol alpha squared is the thermal diffusivity constant, measured in meters squared per second, which tells us how easily heat spreads. The term U sub T shows how fast the temperature changes over time, while U sub XX shows how the temperature is distributed in space. If the diffusivity constant increases, the heat spreads much faster through the material. With our formula established, let us apply our core assumption to see what happens. We are setting out to guess that the solution U is the perfect product of a spatial function x and a time function t. To use this in our equation, we need to find its partial derivatives. When differentiating with respect to time, the position function acts exactly like a constant number. So the time derivative is simply x times t prime. Similarly, the second spatial derivative is x double prime times t. We then substitute these newly found derivatives directly back into our original heat equation. This sets the stage for our next crucial algebraic step. Continuing from our substitution, we now have an equation where position and time variables are mixed together on both sides. Our immediate goal is to isolate them. By dividing both sides by the product of alpha squared, x and t, we achieve something mathematically beautiful. The left side now depends entirely and exclusively on time, and the right side depends entirely on position. How can a function that only changes with time always equal a function that only changes with position? Logically, this is only possible if neither side actually changes at all. They must both equal the exact same constant number, which we call k, the separation constant. Before we move on to a full example, let us visualize what we just achieved mathematically. On the left, you see a complex, multidimensional surface representing a full function. By applying the separation of variables, we break this intimidating surface down into two simple one-dimensional curves, shown on the right. One curve represents the spatial shape, and the other represents the change over time. By multiplying these simple curves together, we can perfectly reconstruct the original complex surface. Now that we have a visual understanding of the separation constant, let us put this method to work on a concrete problem. We will tackle a first-order partial differential equation. The approach remains exactly the same as our heat equation derivation. We will begin by assuming our solution is a simple product of two independent functions, one for the x variable and one for the y variable. We will find their partial derivatives, substitute them in, and use algebra to physically separate the variables. Finally, we will solve the resulting ordinary differential equations to build our complete answer. Here is the specific equation we will solve for our first example. We have the partial derivative of u with respect to x minus the partial derivative of u with respect to y set equal to 0. Conceptually, this equation describes a system where the rate of change in the x direction perfectly balances the rate of change in the y direction. The symbol u sub x is the change along the x-axis, and u sub y is the change along the y-axis. If the rate of change in x increases, the rate of change in y must also increase by the exact same amount to maintain this zero balance. We start by stating our given information and our goal to find the function u. We choose the separation of variables approach because the equation is linear and homogeneous. First, we assume the product solution. Taking the partial derivatives, the derivative with respect to x becomes x prime times y because y acts as a constant. Similarly, the y derivative is x times y prime. We substitute these directly into our original equation. To isolate the variables, we move the negative term to the right side by adding it to both sides. Continuing with our algebraic rearrangement from the previous step, we divide both sides of the equation by the product of x and y. This algebraic maneuver successfully separates the variables. The left side of the equation is now entirely about the variable x, and the right side is entirely about the variable y. Because these independent variables are equal to each other, they must both equal a shared constant number. We define this shared number as our separation constant k. This gives us two separate simple ordinary differential equations to solve in our next step. For our final steps, we solve each ordinary differential equation using standard calculus. The solution to this specific type of equation is an exponential function. For the x portion, we get an arbitrary constant a times e to the power of kx. The y portion similarly yields a constant b times e to the power of ky. To find the final solution, we multiply these results back together. The exponents add up and the constants a and b combine into a single new constant c. This final equation perfectly describes the behavior across the entire two-dimensional plane. Having successfully solved a first-order equation, let us look at a physical application. A vibrating string, much like a guitar string. The string is firmly fixed at both ends. We will again assume a product solution where space and time are completely independent functions. However, because the string is tied down and cannot move at its ends, we will discover a special rule about our separation constant. The constant must be a strictly negative number. This is mathematically crucial to create the oscillating, repeating waves we expect to see in real life. The physics of this vibrating string is governed by the classic wave equation. Conceptually, this formula relates the acceleration of the string to its physical curvature. The term u sub tt represents the second derivative with respect to time, which is the string's acceleration. The term u sub xx is the second spatial derivative, representing the string's curvature. The letter c represents the physical speed of the wave traveling along the string, measured in meters per second. If the tension in the string increases, the wave speed c increases, causing the string to vibrate much faster. We are asked to set up the separated ordinary differential equations for this string. We choose our product solution and substitute it into the wave equation. This gives us x times t double prime equals c squared times x double prime times t. We separate the variables using algebra, just as before. However, we specifically choose to set them equal to negative lambda squared. This guarantees a strictly negative number. If we chose a positive number, the math would predict the string stretches to infinity, which is physically impossible. For our final step, we take our separated equations and rearrange them into standard formats. The spatial part becomes x double prime plus lambda squared x equals 0. This is the simple harmonic oscillator equation, which produces sine and cosine waves that draw the physical shape of the string. The time part similarly rearranges to t double prime plus c squared lambda squared t equals 0. These time-based waves describe exactly how fast the string moves up and down. Multiplying these together gives engineers the complete mathematical model. We have covered a lot of ground today, so let us summarize the most important ideas. The separation of variables method is a clever algebraic trick that transforms intimidating partial differential equations into manageable ordinary differential equations. It relies entirely on the assumption that the final solution is a simple product of independent functions. By isolating variables, we find a shared separation constant that links them together. You now understand the absolute foundation for solving mathematical models of heat, waves, and the physical world. Great job!